So today we're doing two sessions on recursion, and they kind of build on top of each other very nicely. One thing that I would say about recursion is it is kind of tricky to understand, especially if you're seeing it for the first time. And so if you are working on this now and you're like, wow, like this is not making sense, like as of this by the end of this class, don't freak out about it. The two things I always say are one, recursion will definitely come up in your admissions interviews, but it's by no means like the make or break problem. It's not like, oh, if I don't answer this perfectly fine, like I've kind of failed or there's no point in me moving forward. Usually during the interviews, they want to work with you. Ultimately, their goal is to admit you, not to reject you. And so if they can see that you're thinking about it the right way, you're making good progress, you understand the context of what's going on, like they'll work with you and they'll give you kind of, I guess, partial credit or credit for kind of understanding the concepts, even if you're not able to apply it, fully 100% of the way. The second thing is recursion is also something that takes quite a decent amount of practice. It's not something that you can just kind of use kind of arbitrarily. And in fact, in the real world, recursion is used probably not as often as it may as or rather, we don't use it as much as kind of people teach it. And the reason why is because it is very dangerous and is very tricky. And so usually there are ways to do problems without a recursive method, and folks will usually go for that over recursion. But obviously there are some problems that only recursion can solve, which is why it is kind of a seminal topic. Okay, so recursion. We'll talk about kind of what recursion is, and we'll do a few simple examples. Most of which will help us. Most of which will revolve around this idea of a call stack. And then we'll go through a few sample problems that use basic recursion. Just note, for this morning's problems and examples that we use, you might look at it and think, wow, I can do most of these with a for loop. And the answer is yes, you can. So not every problem that we use recursion to solve has to use recursion. But for now, for the purpose of this class, because we're trying to teach this concept, if you could try to use a recursive method as opposed to an iterative method, like with a loop, that would be preferred. Okay, so the easiest definition for recursion that people always the easiest definition for recursion that people always say is, oh, a recursion is a function that calls itself, and this is to an extent kind of true. It's an alternative to iteration in some cases, but in other cases, it's probably the only or definitely the best solution. And once again, right, people use recursion because they have some functionalities that make it really easy to understand. When you look at a recursive functions tend to be actually fairly simple in what they're doing. Remember how earlier when I said a function really should be designed to do one very small, very specific thing. If someone looks at it, they should be very clear what it's doing. Recursive functions probably needs to follow that example more so than other functions because it does have the potential to be called kind of infinite times. You want to be very clear in a recursive function about what is the one key action that I'm really taking, and what am I doing. And then when we talk about recursion, oh, sorry, I'm just bad with this morning with the slides. Okay, when we talk about recursion, the other thing I also want to just kind of have you keep in the back of your mind for now is, once again, recursion is something that is somewhat dangerous to use in a production environment. If the recursive function is written correctly and it works, it's very elegant and it can be very kind of effective. If it doesn't work, it has the potential to bring down other parts of servers too. Because if you think about the idea of recursion being a function that calls itself over and over again, well, in the worst case scenario, it doesn't know when to stop. And if that recursive function is doing something bad, then you're essentially doing it, infinite times or until your computer's memory runs out or something else. So, it is a solution, but by no means should you think, oh, wow, every problem I do from now on should be in recursion. In fact, it should be the opposite. You should only use recursion when you feel like there's a very valid use case for it that you can't kind of mimic otherwise. Okay, so we'll talk about the call stack now, which is very important for us to understand recursion. Line 3 there, JS is single-threaded and can only run one function at a time. We really see this quite clearly in almost every piece of code that we've written so far in this class up to this point, right? When I have a piece of code that runs from line 1 to line 100, like when we walk through it, we say, like line 1 is going to execute, then line 2, then line 3, then line 4, right? And there's a very set order. And in fact, the other assumption that we've also been kind of implicitly making when we were looking at that code is line 2 can only run once line 1 finishes, right? Line 1 and line 2 are not running concurrently. If I say let x equals y and then console.log out x plus 6, we run x equals y first, right? Or if x equals a number and y equals a number, we're trying to add those two numbers together, we have to write let x equals blank, let y equals blank, and then we add them, right? JavaScript will not move on to the subsequent line until this current line has finished. That's what we mean by single threaded. It can only do one operation at a time, and before it moves on to the next operation, this current operation has to conclude or be finished. One analogy you might hear very often when we're talking about the call stack is this idea of kind of a stack of plates, right? Or rather, a stack of plates at a buffet line. If you've ever been to a buffet line, you realize all the plates are stacked upside down, right? But they're also stacked on this kind of like rack thing. And whenever someone comes by and they're like, "Hey, I need to grab a plate," what you do is you take one off the top of the stack, right? Similar, and I guess you probably don't want to do this at a buffet, but if you want to put your plate back, you also kind of put it back on top of the stack. And that's very much how a computer operates too. And that a computer is going to have a list of things it needs to do. But when it has something to do, it will add the job, if you will, as a plate. It will add it to the top of the current stack. And that becomes the thing that it works on. Because the next time it says, "Hey, I need to do something," it will go to that stack. It will see what's on top and take that plate off and start working on that plate or start working on that task, right? So if a computer is saying, "Hey, I have 10 things I need to work on," the first job that it puts on that stack becomes kind of the lowest level, and the next plate that we put on the stack is going to supersede it, right? Because the next time we take a plate off that stack, it will be the second plate we added, not the first one. So so it follows this concept we call like LIFO, last in, first out. Like whatever the last thing you put on the stack is the first thing you get when you pick something up from that stack. When you pick something up on that stack again. So when we look at this function here, we have a first function, we have a second function. When we console log this out, on the call stack, the first thing the computer does is that, okay, great, let's go through this. Lines 5 through 7, I'm defining something. Lines 9 through 11, I'm defining something. Line 13, great, my first actual invocation. What am I doing? I'm calling first, right? So now my call stack, my job queue, if you will, has one thing, and it's this first function. And the console logs out, I am first, right? Remember, line 14 can't run until line 13 finishes. That's why this is going to run. That's going to console log. And once this is done console logging, I am first. Hey, I'm done with the first function, right? That job is complete, right? I can take it off my to-do list. And now as a computer, I have a blank to-do list. Like, great, give me my next job. Give me my next call. Give me my next plate, if you will. The next plate is a function called I am second, and I'm invoking it. So when we go to this when we go to the second function, it's going to console log out I am second. So once we're running this job, we console log out I am second. We are now done with the second function. We take that off our to-do list, and now we have a blank call stack. And in fact, our code is finished, right? There's nothing else on the page. There's nothing else for us to do, and we've done the two things we were supposed to do in sequential order. Okay, so this is everything we've seen so far, just probably a little bit more granular. But every piece of code we've ever run follows this pattern. And if you may notice, the thing that we're always doing is we're saying, hey, here's a call stack. I'm giving you a function. I finish it. I move on to the next function, right? So when would this ever build up? And that's where we start seeing, and that's where the idea of recursion really kind of starts to take root. Is that, well, a lot of times functions aren't as simple as just saying throw a console log out and you're done, right? Usually there's more to it. And so let's take a look at some more examples here. Okay, we have a function called first. We have a function called second. The second function hasn't changed, right? It's very simple, very straightforward. Just console logs out a simple message. The first function, on the other hand, console logs out message. Then it actually invokes this second method within the first method, and then it console logs out first is finished. So if we look at what happens when we actually run this function, once again, we only have one invocation there on this entire page at the outermost scope, if you will, and that's on line 11. We invoke this first method, and so our call stack, once again, we throw this first method on there, right? Well, if we throw the first method on there, let's go through it. Step 1, console log out I am first. Great, done. Step 2, invoke second, right? And now here's where we see this call stack. We actually add the second on top of the first call stack because guess what? First isn't finished yet. And in fact, by definition, we cannot finish invoking the first function until we finish invoking the second function, right? So even though so this is like the principles of last in, first out. Even though this second function was kind of added to the queue after first, it immediately becomes the next highest thing, right? If these were plates, I put the first plate on here, then I put the second plate on here. The next time I need to take something off that plate stack, I'm taking the second plate, right? I'm taking the first thing on the stack. And so going back to this code now, on line 3, we're invoking second. We're not invoking it in parallel to first. We're saying, no, first needs to finish running second before first can finish running itself, right? It's almost like a dependency. It's like saying, I can't finish until I do everything, and this second function happens to be one of those things. So now we have a call stack, and now the call stack says, okay, what's my priority queue? The most important thing to work on right now is invoking second. Okay, let's jump to invoking second. Second just console logs out the I am second message, which comes up here. And once we finish logging that, we're done with second, right? So once we're done with the function, once the function reaches the end of, I guess, the code block, we can say, okay, second has been resolved, right? We now take it off our call stack, and then we say, all right, what we were doing before we kind of took this segue to second, oh yeah, we were working on first. And where did we leave off? Well, we left off at second. We finished it, so now we can move on to the next line in the function, which is finished. First is finished. And that's what we see printed out there. And now we're also done with first as well. So this goes off our call stack. And for a computer, this is like nirvana. This is great, right? I want to have an empty call stack where I've finished everything you've given me in the correct order, and I'm done. Any questions on this? Pretty straightforward, right? Like, it makes logical sense if you think about a computer just kind of saying, if a computer is very binary, it's like, what do I do next? This, or this? Like, great. Okay, so if we want to think about a function that that counts down from a given number to 1, one way we can do this is obviously through a for loop, right? And hopefully by now this for loop is going to be, it's almost table stakes. You can kind of recognize it pretty easily, right? Except this time, rather than incrementing by 1, we're starting at I equals num, and we're saying, hey, stop when you get to 1, and we're decrementing the number each time. So we start I equals num, in this case I equals 5. Is 5 greater than 1? Yep, log out the number. Then let's decrement 5 by 1, so now we have 4. Is 4 greater than 1? Yes, and so on and so on, until we print out 5, 4, 3, 2, 1, right? Very simple for loop, nothing special about it. But if I was to do this now, if I was thinking about doing this a different way, one way to look at this is thinking about, okay, if I have a problem, right, and it's clear I'm doing the same thing kind of over and over and over again, let's think about another way to represent that. Well, if my goal was to count down from 5 to 1, if I have a function that just does one very specific thing, which is I give it a number and it prints it out for me, this, between lines 8 through 12, this is an equally valid way to get the answer, right? It's a lot more cumbersome, it's a lot more heavy for sure, but it still gets us the output that we want, right? What's bad about this solution, obviously, if the number is 100, we now have to copy and paste this 95 more times, right? But it still works, right? And in fact, the main thing I want you to draw attention to is that, like, hey, we're just having this one function do this one very specific thing over and over and over again. And between each time we ask it to do it, the only thing that's really changing is what in this function? There's no I on this.
Oh. The argument?
The argument, the number, right? The function is going to be constant. The function does the same thing every time, right? The only thing that changes is we give it a different number each time, right? And in fact, in this case, we're giving it a smaller and smaller number each time. So every time we call countdown, we subtracted 1 from the previous number. And in fact, this kind of begs the question, well, if I know this pattern exists, why not just have an outer function call the countdown? Or why not have the countdown function keep calling itself until it reaches a certain point? So if I think about something like this now, okay, I have my countdown function still, right? I still give it a number. And on line 8, I still log out that number. But when I do this, after I log out the number, I do countdown of the number minus 1, right? When I do countdown the minus 1, I'm like, if this instance of the countdown function is running, when I call line 9, pretend like another instance of the same function pops up, right? Except now this time it's going to be countdown, and the number is going to be what? 4, right? And so it's going to console log out 4, and then the next line after that is saying, hey, let's do another countdown of 4 minus 1. So another instance of the countdown function pops up again, starts running, right? Except this time we're running countdown of 3. So let's see how this looks from a call stack perspective. We start. Sorry.
We don't have an ending though. Yeah. Would it just?
Yep. Well. Yeah. Spoiler alert. This is gonna break. So until it breaks, let's see how this is gonna happen for the first couple of iterations, right? We start on line 12 with our countdown of 5, right? That hasn't changed. And to do countdown of 5, we're saying, okay, great. Let's go to line 7. All right, cool. I've created a num. It's going to be 5. Line 8, I console log out 5. Great. Nothing special so far. Next thing I got to do, countdown of 4. And remember, I have to finish running countdown of 4 before I finish running countdown of 5, right? Countdown of 5 cannot finish. I'm not going to reach this end curly braces for countdown 5 until I finish doing whatever countdown 4 is doing, right? So that's why this countdown 4 goes on top of countdown 5, right? I'm not clearing this away. I'm saying, no, before this finishes, I have to finish doing countdown 4 first. Well, countdown 4 is going to log out 4 for me, and then it's going to say, by the way, before countdown 4 finishes, I have to finish doing countdown 3, right? So now you see the stack's building up, right? Countdown 5 can't finish until countdown 4 finishes. Countdown 4 can't finish until countdown 3 finishes. And to Sarah's point, we can say, okay, let's keep going. Great, awesome. Oh crap! Like this is actually going to keep going infinitely, right? Right? Like at no point you ever stop. We just keep going, and obviously a number can be infinitely negative, right? There's no stopping it, right? So you can see how. Yes, I started this by doing countdown 5, but notice how everything kind of builds up on it. And so when I say something like, "Oh, your computer's going to run out of memory," this is what I mean, right? The computer is going to call itself over and over again, which in itself is not wrong, except if you're sorry, except if your countdown never finishes, then what's going to happen is you're going to try to juggle almost an infinite number of operations at a given time, right? And so your computer, just as a quick detour, only has so much memory to hold for the jobs it's currently doing, right? And if this thing says, hey, here's like a million or a trillion jobs, the computer can say, okay, I can't handle all of that. I'm going to throw an error. Modern computers are better at this, right? If they see something like this, they'll say, okay, it's probably a human error and not you legitimately have like a trillion things for me to do. So modern computers are pretty good at kind of figuring out or detecting when something like this happens. And the error that you usually see is something called maximum call stack size exceeded, which means, look, like you just have way too many things when you do a given time. If this is if this is a legitimate use case, either you want to kind of reparse it out, or you want to get a bigger computer, right? But essentially, that's kind of like recursion gone wrong, right? You call yourself, but you really don't know when to stop. Cool. All right. So with recursive function, the big thing that like it's almost like writing a while loop. Remember when I talked about writing a while loop, right? The idea of a while loop is, hey, there's a condition, and when you write your while loop, you need to be absolutely sure that at some point your condition becomes false, right? Otherwise, your while loop is going to run infinite times, just like how we saw that recursive function runs, right? So for things that have the potential to run infinitely, like obviously the biggest, most important aspect of this, well, when do you stop, right? Because very rarely, or actually never, do we want things to run infinitely, right? So when do we stop? And when we talk about recursion, there is a condition that usually kind of tells us when to stop the function, and it's colloquially called the base case. But you can just think of it as almost like in the same way that a while loop has a certain goal it's trying to hit before it stops. With the base case, the idea is every time your function calls itself recursively over and over and over again, it gets closer and closer and closer to the base case. And once it reaches a base case, it actually has to stop, or it actually will stop. And that's going to put a limit on how many calls you're juggling at a given time. So what's our base case? Well, the idea is that in this case, we're trying to count down the numbers from 5 all the way down to 1, right? So really, the last number that we print out should be 1. And if the number is 1, it means our function is kind of done its job, and we don't want to have it print out 0, then -1, -2, and on, right? And so in this case, our base case is going to be, hey, when num reaches 1, or in this case, when num is less than, or when num is less than 1, let's just print a message saying, hey, I'm good. We're done, right? Because once num hits 0, do you want to keep calling the function over and over again? You don't, right? Like there's nothing else to do. Like our function has kind of run its course. When we did the for loop, we did I is less than or equal to 1, right? We also done I is less than or equal, or I is equal to 0 or something, right? Same idea. We're just saying, hey, when do I stop? Well, I stop when that happens. Okay. Now let's do a shorter example. Countdown of 3. I do countdown of 3. Great. It's going to go through this countdown function from line 1, right? Num is 3. Is 3 less than 1? The answer is no. Great. So we go to our else statement. On line 8, we console log out num, okay? And then on line 9, we're calling countdown with 3 minus 1, which is 2, right? And once again, countdown 2 has to finish before countdown 3 can finish, because countdown 2 is part of countdown 3. Countdown 2, is 2 less than or equal to 1? No, we log out 2. And now we're calling countdown 1. Okay? Countdown 1, is 1 less than 1? No, it's not. Let's keep going to our else statement. Let's console log out 1. And now on line 9, we're finally saying countdown is 0, right? And at this point, we go through this function one more time. And we say, is 0 less than 1? Yes, it is. Great. We print out done. Is there anything else we need to do for countdown of 0 here? Yay, nay? Yes, no? No, great, thank you. Yeah, we're done, right? If num is 0 and I go through this function, it's an if-else statement, right? If num is 0, I hit this if clause, otherwise I hit this else clause. If num equals 0, I execute line 4 and my function's done, right? There's nothing else to do. So I can now do what? I can take this countdown 0 off my call stack, off my job queue. I finished it. I've done it, right? I finished doing this one thing. Great. And so what does that mean when I finish the countdown 0? It means, all right, great. Where did I leave off? I left off on countdown 1. When I was doing countdown 1, what was I waiting for? All right, I was waiting for countdown 0 to finish, right? Once countdown 0 finishes, I look at my code. It's like, okay, great. There's nothing else for me to run in countdown 1. I'm done with that as well, right? So then I can also take this countdown 1 off of my to-do list, right? And the pattern's going to repeat. What was countdown 1, or what was countdown? The next thing on my to-do list was countdown 2. What was countdown 2 waiting for? It was waiting for countdown 1 to finish. Well, we just said we finished it. We took it off our to-do list. So countdown 2 is also done. And then same pattern applies. We finished countdown 3. Oh, no. Ugh. And we reach our happy state, right? Every single function on this page has been called and finished. Countdown 3 is done. We got the message that we wanted, and we're good, right? The computer's like, okay, I'm done executing this. Let's move on. So the base case is extremely important because the base case essentially tells you, hey, you're gonna call yourself until when? Until when the base case is reached, right? And usually when we look at this code, right? If countdown was both in the if clause and the else clause, it probably means you're doing something wrong, right? In this case, it's very clear, right? The function is the only time countdown calls itself is in this else clause. In the if clause, it doesn't call itself, right? And so when I look at this code, the idea is like, if I hit my if, I'm not going to call myself again. If I don't hit my if, I hit my else, then I'm going to call myself. So that's one way of presenting a base case. Any questions? Cool. Yeah. So the two takeaways: we need a base case, and we must be getting closer and closer to hitting the base case with each with each successive run of a recursive function. Okay, so yeah. So don't worry about these for now. Okay, so let's do one more example. Define a function, a factorial function, and just to recap, factorial basically means, hey, let's multiply. If I give you a number and I want the factorial of it, it just means multiply this number for every number less than it until you get to 1. Okay, so 5 factorials is 5 times 4 times 3 times 2 times 1. 4 is 4, 3, 2, 1, so on and so forth, right? So that's kind of how the math behind it works out. And of course, we could do this with a for loop, right? Wouldn't be that hard. We just have we have to have a let count equals 0, right? We go through the for loop, and then at each specific thing we increment it by, or rather we multiply that by the number in the for loop. But let's try doing it recursively, because this also is something that at a quick glance you're like, well, I'm doing the same thing over and over again, right? Why not do it recursively? It's probably a terrible way to think about it, but okay, so factorial, num. Once again, we're starting, and this is obviously an oversimplification here. We're starting with our base case. What's our base case? Well, every number that I want the factorial of, I'm going to multiply that number by what? By the number smaller than it, right? Until when? At what point do I stop? Until I reach either 0 or 1. And we'll see why those two are both there in a little bit. But once again, this is super critical, right? This is our base case. This is telling us, hey, I have this factorial function. Even if it's recursive, as soon as I hit 0 or 1, I hit the return statement. And the return statement is what? It's a constant. It's a number, right? Return, once again, gets you out of not the nearest set of curly braces. It gets you out of the nearest function set of curly braces. The nearest function scope. It gets you out of the function. So I know that when I hit num equals 0 or num equals 1, I'm done with this call of the factorial function. So I know I have a stopping point. So when I call factorial 0 or in factorial 1, I get 1 and 1. Okay, really simple, really dumb, but this just makes sure that works, right? Okay, so let's try to be a little bit more, like, recursive thinking, if you will, on this, right? Well, if we have our base case, what does factorial really mean then? If we noticed earlier, factorial 0 is 1, factorial of 8 is 1, or factorial 0 is 1, factorial of 1 is 1, okay? Factorial 2 then becomes 2 times 1, which happens to be also the factorial of 1, right? 3 factorial then becomes 3 times 2 times 1, but hey, we've already calculated 2 times 1 up here, right? And it's a factorial of 2. So 3 factorial is equal to 3 multiplied by the factorial of 2. And then 4 equals 4 times 3 times 2 times 1. But hey, we've already calculated 3 times 2 times 1 right above it, right? Which is 3 factorial. And so here we're starting to see a pattern here, right? Where we're actually able to leverage the factorial function over and over and over again. So this is the part where it gets a little bit tricky. Okay. So let's say let result equals factorial of 2, right? What's going to happen here is we're going to put 2 as an input. We're going to say, is num equal to 0 or 1? And the answer is no, right? So then we hit here, line 6, line 7. There's not really any code to execute. And so then we return what? We return undefined, right? That's what it is, right? Remember, every function returns something, right? If it was 0 or 1, we return a 1. Otherwise, I don't have a return statement, so I'm return undefined. And so that's why on line 13 there, result is undefined. But what I also know is this. If, on the other hand, if I know that I will, at every single stage, what I want to do is I want to figure out what the recursive, or rather, I want to figure out, okay, for me, like, what's the factorial of the number 1 less than me, right? Because if I know, if I go back to my previous slide, right, which is this one, or no, where is it? This one, right? If I know the factorial of myself minus 1, then all I got to do is multiply by myself, and I have my answer, right? It's pretty straightforward there. So the goal really is trying to figure out what the factorial of myself minus 1 is. Okay, so here we console log out factorial of num minus 1. And now if we do factorial of 2, what do we get? Well, so here the first console log corresponds to line 9, right? Which is, well, the factorial of 2 minus 1 is factorial of 1. And factorial of 1 is going to give you back a 1. The undefined is still here because, once again, notice how in our factorial function, if the number is not 0 or 1, we still don't have a return statement. So we're still implicitly returning undefined, right? However, if we now actually apply the math that we just did, which was, hey, for every given number, like my factorial is myself multiplied by the factorial of myself minus 1, voila, I start getting closer and closer to kind of where I need to be, right? And notice how, once again, lines in the factorial function, unless a number is 0 or 1, we still don't have a return statement, right? Right? We still have nothing here. We have a console log, which once again means nothing. It's just a nice to have, nice printout, but doesn't do anything. So the simple answer is, well, let's just return that, right? Let's return ourselves multiplied by ourselves minus 1, and we get 2. Okay, so this is the answer, and let's see if the next slide actually, yeah, great. So let's try to walk through this answer now within the confines of the idea of a call stack, right? In this call stack, what's the first thing that gets put on our call stack? If I was to just run this code on a computer,
Factorial of 5.
factorial of 5, right? That's our first thing, factorial of 5. When we run factorial of 5, we're checking. Okay, great. Is 5 equal to 0 or 1? No. Okay, let's move on. Okay, line 7. I'm trying to calculate out 5 multiplied by factorial of 5 minus 1, which is 4. Okay, great. Well, that means I need to figure out what? I need to figure out what factorial 4 is, right? Great. So now I add factorial 4 to my call stack, and if I go through this function one more time, or rather, I'm not going through this function one more time, I'm creating another instance of this function, I'm going through it top down. Factorial 4 is 4 times factorial 3, and obviously I have no idea what factorial 3 is, so got to figure that out first, right? Factorial 3 is 3 times factorial 2, don't know what that is. And then finally we have factorial of 2 is equal to factorial of 1. Okay? Factorial 1, great. Let's figure out what factorial of 1 is. Well, if num equals 1, what does factorial give me back? A 1, right? And then I return a 1, and so do I do anything else here? Well, yeah, so I'm like, once I get the 1, like once I get a return value, my function is by definition done, right? As soon as I hit a return, like, it doesn't matter what else is written after at this point. Like, return says the function is done, here's your value, go home, right? So I get my 1 as a return value, and by definition, factorial 1 has to be done. Nothing else isn't factorial 1 is going to run anymore, right? So factorial 1 becomes just 1. So let's plug this 1 back in here, right? Factorial 1 is finished running, and so let's see, where do we leave off? Well, we left off with figure out what factorial 2 was, and it was dependent on, and the math behind factorial 2 was 2 multiplied by factorial 1, right? From line 7 here. So let's slot this value in. What's 2 multiplied by 1? It's 2. So now we're still trying to finish factorial 2 here, right? We get to line 7, result is equal to 2 times 1, which is 2. And then line 8, we return 2. And what else do I have to do for factorial 2? Nothing, right? I'm done. Once again, I returned a value. By definition, I'm done with this function. Well, factorial 2, why did we have to calculate factorial 2 again? Oh, right, because factorial 3 needed to know what factorial 2 was before we can move on with factorial 3. So we take this 2 now, we slot it here, and now factorial 3 says, okay, let result equals 3 times 2, which is 6. Let's return that 6, and boom, we're done with factorial 3 too, right? And so if we keep going this pattern through it over and over again, by the time we get back to factorial 5, our initial function, we're going to say, hey, you know that factorial 4 you wanted? It was 24, right? So then what's 5 times 24? It's 120 on line 7. Line 8 says, Great, return the 120. And then where do we return the 120 to? Where does the function return the value? I'm sorry? Right. It returns, remember, functions return values to whoever called it or where it was called, right? Where was factorial 5 called? Right here, right? So we slot in 120 now for factorial 5. So line 11 becomes let result equals 120. And so when we console log out result, we get 120. It seems cumbersome, but this is a very valid way of doing the same problem, right? At every instance, like if you just kind of take a step back and think about it from a macro perspective, like what this recursive function is really doing is saying is, hey, look, like I don't need to do that much math, right? I'm gonna just, you know how like when we were talking when what was it? I think yesterday someone was talking about reversing an array, right? Like what you're really saying is, hey, let's just like let me do like the one minimal thing I need to do, and I'll let the function take care of the rest, right? Or rather, I'll let someone else take care of the rest, right? Imagine if you have 10 identical people trying to do the same job, and they had to, let's say install like 10 nails, right? The first worker just says, hey, let me put my nail in, and here you guys go. Why don't the 9 of you install the next 9 nails, right? The next guy or next person installs a nail, says, okay, there's 8 more nails, there's 8 of you, go ahead with it, right? And so at every single stage, you're getting closer and closer to the end, but you don't quite worry about it, right? When you write one function that runs top down straight through, you need to worry about like on step 1 I'm doing this, step 2 I'm doing this, step 3 I'm doing this. Here what you're really saying is you're breaking down the problem into smaller portions, right? If I could describe this factorial function verbally, all it's saying is, hey, look, if I'm 0 or 1, I know I've reached the end of the road, just give me back a 1. Otherwise, let's just take myself and multiply by the factorial number less than me, right? What's the factorial number less than me? I don't care. The factorial will figure it out, right? And the next factorial takes that number and says, am I a 0 or 1? If it is, I'll give you back a 1. If not, then I'll just give you back myself multiplied by the factorial of a number less than me. What's that value? I don't care. The next guy will figure it out, right? And so we just kind of keep passing the buck further and further along until until at some point it's going to hit this, oh, num is 0 or num is 1. And we say, oh yeah, like there's nothing to pass back. There's nothing else to do, right? Just here's a 1, right? And then every person kind of passes it back up the chain of command again to get to the final value, right? So it's a way of thinking, but it's also a very valid way to do this problem. Okay, any questions so far from just the examples that we've seen? Are people kind of conceptually kind of understanding a little bit at least of kind of how recursion is supposed to work now? Okay, so to wrap this up, a few kind of big things about factorials. One, always use the base case. If there's no base case, your function is going to crash your computer. For this one, I would especially recommend you use REPL to code the problem. I think CodePen handles like infinite loops poor, or rather it does something like kind of weird to it. So I would definitely use REPL. I think REPL is more adept at just kind of throwing the error back at you as soon as you try to run something that's an infinite loop. Two, once you write your base case, like test it to make sure your base case actually works, right? Like don't just write a base case like, oh, I hope this works. Like no, like if it doesn't work and you run your loop the first time, it's going to break, right? And then 3 is always try to test using smaller inputs whenever possible. Like when we did our countdown function or we did a factorial function, could I have tested with factorial of 100? Yeah, I could have, but it would take me forever, right? Because there's been a lot of math for me to work through, right? Usually the idea behind the idea of a recursive function is check your base case, check that it works for 1 plus your base case or like one thing on top of your base case, and then everything after that should almost work identical to like 1 plus your base case, right? So you want to check your base case and you want to check like a very small marginal increment on top of your base case, and that's pretty much all you really should need to do, assuming your function is written correctly. Okay. Yeah. Okay. Yeah. So this is telling like a lot of the ways that you can do recursive programming. You can also do with iterables, which are just like for loops, kind of typical loops that we've already seen, are more comfortable with. Start with base case, test with smaller cases, and then also And I know like or yesterday at least, we kind of started becoming a lot more strict with the return value, right? Return is not something that we can just now kind of casually use interchangeably with console logs, because guess what? If I console log out something, the function that called me doesn't get any values back, right? Or rather, it gets back undefined. If I use a return value, it actually gives back that value. So we really want to be careful now about like what we're returning. And in fact, if you have a function and you're like, oh, this doesn't give what I want to do, if you delete all the console logs from your function and you look at it, does it still look like it's doing what you want it to be doing? It's a good test case. So that's pretty much it for recursion 1. We'll do more recursion in the afternoon session, but as of now, any questions on recursion? Yeah, Sophie?
Which approach is faster, recursion or for loop?
For a lot of things, they're probably the same. It's not really or for the examples that we're going to look at, it's not really a speed boost. Like I said, for this morning's workshop, every problem that you can do either way, and they'll probably both be equally as fast, which is probably imperceptible to humans. In the afternoon, we'll see certain problems that can only be done with recursion. So it's more like you can't do this as opposed to, oh, this is like better. Any other questions? All right. I will psych out pairs, and I will set up bagels, and then you guys can do problems and eat bagels.